In mechanics, failure theories are used to predict the failure of material under different loading conditions. The failure theories provide criteria for determining when a material will fail under various stress states. For an engineer, it is important to place an upper limit on the stress state that defines material failure. The material can be either ductile, where the failure is initiated by yielding, or the material can fail in a brittle mode where the failure is specified by a fracture. These failure modes can easily be defined when a component is subjected to a uniaxial state of stress, as in the case of simple tension. Nevertheless, in the case of biaxial or triaxial stress states, the criterion for failure becomes more challenging. Therefore, the theories of failure become relevant, and they help us to predict the failure of materials subjected to multi-axial state of stress. However, one thing must be kept in mind. There is no single failure theory that can be applied to a specific material all times. The reason is that a material may behave in either ductile or a brittle manner, which is which might be due to a particular temperature or rate of loading or chemical environment, etc. For the theories of failure, it is important to find out stresses or strains at a point. These stresses and strains include normal and shear stresses. In the case of failure theories, it is important first to find out the normal and shear stresses at the point, especially where there are largest concentration of forces. Once a particular state of stress is established, then the principal stresses at that critical point can be determined, and correspondingly they can be plugged in the failure theory to get the particular failure mode. So let us now discuss two important failure theories. The first one is maximum shear stress failure theory. The maximum shear stress theory is also called Tresca theory. This theory states that the failure occur when maximum shear stress in a material exceeds the shear strength of the material. It assumes that yielding begins when the maximum shear stress reaches a critical value independent of normal stresses. Hence, this type of failure occurs in ductile materials. So, steel, for example, can be designed based on maximum shear stress theory. In the case of steel, the yielding of material is caused by slipping, which occurs along the contact planes of crystals that are ordered randomly. These are those crystals which make up the material. This is shown in this figure where we have occurring at 45 degrees. The maximum shear stress in this case can be found by drawing a Mohr circle. So in this figure, we have a Mohr circle drawn for a particular state of stress. This rate of stress tells us that there is only axial tension stress shown in the adjacent figure and no stress in the other orthogonal direction. Hence, the maximum shear stress will be equal to sigma y by 2. Another case, if we have biaxial in-plane stresses of opposite sign, then using these stresses, we can also draw a Mohr circle. In this second case, our maximum shear will be equal to sigma 1 minus sigma 2 by 2. Thus, using these Mohr circle, we can determine the failure occurring when the maximum shear stress at any point in material exceeds a critical value. That critical value is known as the shear strength of the material. The other well-known theory is called maximum normal stress theory. This theory is commonly used for brittle material. Brittle materials such as concrete tend to fail suddenly by fracture with no apparent yielding. In a tension, tension test of concrete, failure occurs when the normal stress reaches the ultimate stress. So, in this theory, we can say that the failure will occur when the maximum normal stress at any point in material exceeds a critical value known as ultimate tensile strength or ultimate compressive strength of the material. If the stress coordinates sigma 1, sigma 2 at a particular point falls on the boundary of this shaded area, then the material is classed as a fractured material. Thus, we have sigma 1 is equal to sigma ultimate and sigma 2 equal to sigma ultimate.